Look at a standard mathematical matrix, and you'll usually just see a dense block of numbers. To the untrained eye, these grids look like an intimidating, meaningless jumble of digits. These blocks function as mathematical engines. When a 3D model passes through this grid, those numbers stretch, skew, and distort the geometry. The problem is, looking strictly at the raw figures gives you almost no clue as to how the object will actually warp. In fields like computer science or structural engineering, you can't build reliable software or safe bridges if you're relying on unpredictable systems. You need to know exactly what the math is doing. That is where the tools of linear algebra come in. They act as logical scalpels, allowing us to accurately reverse engineer the math and observe the gears turning inside. Understanding a matrix is entirely about taking a massive, multidimensional problem and dismantling it into observable, foundational mechanics. Before we start tearing a mathematical structure apart, we have to run some baseline diagnostics to see how it naturally behaves. The first diagnostic tool is the determinant. It's a single number telling you if the matrix expands, shrinks, or collapses the physical space. Then we look at the trace. Summing up the numbers straight down the main diagonal gives a quick snapshot of internal stability. Look at these equations. We can solve systems like this using Cholesky decomposition. It only works if the original matrix is symmetric, mirroring itself across the diagonal. With that symmetry, we split the matrix into a lower matrix and its exact reflection. This specific factorization essentially slices the workload in half. Instead of brute forcing one massive computational headache, we tackle two sequential bite-sized steps. By exploiting the natural symmetry hidden in the data, Cholesky decomposition aggressively reduces computational bottlenecks. But that raises an obvious problem. What happens when your dataset is messy, rectangular, or completely lacks that clean symmetry? Look closely at this equation matrix. For everything else, we rely on singular value decomposition, or SVD. It is the universal, heavy-duty method for matrix teardowns. Its underlying logic proves that absolutely any matrix can be broken down into exactly three independent spatial actions. First, V-transpose performs an initial rotation, realigning the raw data along standardized processing axes. Next, sigma executes a proportional stretch along those axes, showing where the data expands. Finally, the U component applies a second rotation, locking the stretch data perfectly into position. SVD takes an incomprehensible mathematical transformation and distills it into a highly predictable sequence: rotate, stretch, and rotate. When we look back at those massive grids of numbers, they stop looking like intimidating black boxes. They become highly readable instructions. This raw data represents a defined sequence of instructions, specific stretches and rotations performed on a coordinate system. These decomposition techniques power the architecture of modern digital processes, from image compression to video game rendering. They also serve as the bedrock for modern machine learning. SVD and Cholesky provide the structural efficiency required to train massive artificial intelligence models on billions of parameters. The utility of linear algebra lies in reduction. It proves that no matter how dense the data, it can always be stripped back to its constituent mechanical actions.